So without further ado, let's dive into it. So as we all probably know by now, large language models from all the way from like ChatGPT to like other large models such as Lambda, they have been showing impressive success performing various tasks, all the way from answering simple questions to engaging in the conversation. So for all of these capabilities are hinged upon having a good prompt for the large language model. So if you have this good prompt, you can perform all kinds of tasks from summarization to code generation to sentiment analysis, all the way from dialogue to translation and to story generation. However, as these language models can also be sensitive to how these prompts are phrased. For example, let's take summarization as an example. You might be able to tell the model summarize this article, and then sometimes, maybe not always, but perhaps it might just not work. How about we change it to something that seems relevant but also quite different, say the summary is, and sometimes it might just work. So here we're talking about like these self-supervised pre-trained language models, and it's a different issue whether like if you want to fine tune it on additional downstream data for it to better perform summarization. So that's another issue. So now we're talking about these massively supervised language models. So given these language models that are known still to be sensitive to their input and to how the prompts are worded, what's the best way to talk to them? In other words, how can we make these large language models do what we want? So this is where like the challenge of finding the best prompt comes in. Let's take this example. Still, summarize this article. Let's say it doesn't work. So one very typical, a very popular approach is to just try to come up with a better prompt manually. So this is where like the latest, hottest job called prompt engineer comes in. Maybe we can invite this prompt engineer to come here and then maybe tweak a few words in this prompt, or maybe write additional conditions like summarize this article, but say like present all the facts in this article. So something like that. And then you might be able to get some quick feedback by running these prompts through the language model. And then maybe this doesn't work. What if we change another word or write some more conditions? And what if it still doesn't work? So what's like a more systematic way to do this because a human can only think of how they might talk to a human about this, but there's never any guarantee that these large language models will be exact replicas of humans. So what are some other ways to do it? Another popular approach that's a step forward from manual design is so-called enumerate and select. So in this situation, the human can take a back seat and having the robot or some kind of computer program to generate a list of candidates in various ways. For example, you might use a paraphrase model to like take a prompt and try to paraphrase it, or you can do an edit. So like you incrementally edit each word in the prompt one at a time. Or some newer methods are like prompt perfect. So maybe you can use a large language model to write a better prompt for you. These are all possible. But invariably, once you have all of these prompt candidates, what you're still going to do is to feed them into this large language model and get some quantification of how good these prompts are. So these quantification might be some kind of score that evaluates the success at certain tasks. And based on the score, you can maybe select some of these candidates. So while this can usually improve the prompt to some degree, there's still no guarantee that you're going to always locate the best prompt. It's because so all of these methods still like use various kinds of heuristics or rules-based methods to simply search in the typical spaces of the prompt that humans will consider that we're simply using some programs to like automate. So based on this, what are some other ways that we can do it? Maybe for which we can have like a better guarantee of better results. So that is where like a more numerical tuning scenario comes in. So So this is usually called prompt tuning. And so here, instead of having a human come up with prompt candidates or like coming up with like prompts in their actual words, we're simply using a series of numbers to represent each word in this prompt. Maybe we can start with their embedding in the language models. After that, instead of the prompt, we simply feed these embeddings into the model and then compute the quantification of the performance, maybe some kind of loss, and then backpropagate through all the entire language model to update some of these prompt parameters. I believe this is not very cutting edge at this point, so probably everyone knows this. So I will quickly go through this. So perhaps you can run it through several iterations. Maybe you get better score, you do some more backpropagation, and then you might get even better results. So this all seems to work so far, but there are also some key considerations for this type of approach. So first off, it's very apparent that this prompt tuning method will yield you a prompt that by like neural network training can usually get pretty good performance. However, these prompts are not interpretable because they are just a series of numbers. So a popular method for interpreting them will be just to map them to like a token that's closest to it in the embedding space. However, there are some words that show that these embeddings don't exactly map to like exactly one token. So even in the close neighborhood of these tokens, of these embeddings, there are a wide number of tokens that are all very close to this embedding, and some of them might be toxic, some of them might not, might be. So this brings some issues into like what's the best way to interpret them. The other one is like in terms of access or efficiency. So for these methods to work, you really have to have access to the underlying neural network of the super large language model. And you have to be able to run backpropagation through them. So you not only need to like be very close to whoever is serving these large models, but you also have to maybe convince them to give you enough resource to not only run inference, but also backpropagation, which will cost additional memory and hardware. And last but not least, these prompts are learned typically in like the latent space of this large language model. And given that different large language models usually have pretty incompatible latent spaces, they might even have different dimensions for their token embeddings. So it will be virtually impossible to learn one prompt for one large language model and try to transport them across to other models and try to attempt to get a similar level or better level of performance. So these are all the possible issues with numerical tuning, despite some of these promises. And in response to this, we present our solution RL-Prompt, where we optimize discrete text prompts using reinforcement learning, where we combine the advantages of various approaches that came before into this single word. First off, we are automatic, so there is no need for a human to intervene and try to think of a better prompt. But we're also systematic in that we don't just use heuristics. We use a more structured guidance from a specific reward signal to have a more fine-grained tweaking of each token in the prompt. We are more accessible in that we don't need access to even the underlying model. We don't need access to the neural network to do backpropagation. The only thing we need is an inference API, which can either take place from maybe even just a Hugging Face model or even just the API of say like GPT-3. So, and also we're flexible in that we support various kinds of tasks from classification to generation or to many other tasks, as long as you can measure the performance. And also we can work with a wide range of models. So from mass language model to infilling to like autoregressive or left to right language models like GPT. So it's all possible. We are also transferable in that because the prompt that we learned are discrete text, it's like a trivial for us to take one prompt we learned from one language model and transport them to other language models and expect them to perform similar tasks, as we'll show later. last but not least, so because we're learning these pre-text prompts, they are trivial to, I mean, they will be so much more transparent to interpret because they are anchored to these specific words that that do not require interpolation in, like, say, an embedding space. And from examining these learned prompt tokens, it will also be possible for us to like get some insights into what are the best ways to talk to these language models, and for which I will show some examples later. So I will start presenting our approach. But before that, I want to maybe talk about this problem in a bit more abstract manner, so that we can derive some insights into the whole prompt optimization problem. So here, let's consider us trying to optimize a prompt for this large language model. Usually, we consider having the prompt and also some kind of input. We send them into the language model to get some output. Based on the output, we compute a score that quantifies its performance. And after that, we try to maximize its performance by tweaking in the prompt space. If we use some variables to represent this process, then we can write this optimization problem. So let's look at this optimization problem for a little bit. We can see that it's optimization in the discrete space, and it can be highly inefficient because the number of your search space will increase exponentially as you increase the number of words you are searching for, and also in the length of the prompt that you're searching for. So let's look at this more concretely. Let's assume that we want to optimize a prompt with 5 words. And in a typical GPT vocabulary space, each word has 50,000 options. So that will be in a total of 3 to the 10 to the 23rd number of candidates. And that's at the same scale as the number of stars in the universe. So it is clearly not feasible to simply go through all the possible prompts and then try to find the best one. And then that's where I believe previous work want to, like, limit the search space. So they search for they want to search in, like, a smaller space where maybe they have a better where they might still expect some level of good performance. For example, one might restrict the search space of prompts to, like, maybe some prompts that humans typically consider to be a valid instruction or like fluent natural language. Or you can like turn this discrete optimization problem into a continuous problem and try to interpolate in the continuous space of prompts as in terms of the word embedding of these prompt tokens. So these are all possible, but the problem with the continuous interpolation is that you are not guaranteed to, like, match to a specific prompt that will have a number of benefits of these discrete prompts. So what are our proposed solution to this problem? So instead, we're also trying to turn this into an easier problem, but we're doing it in terms of reinforcement learning. So instead of searching, like, exhaustively for all the possible combinations of words, we instead try to train like this neural network that can generate this prompt. So we optimize over this neural network and to like optimize for the reward. So here, like, you can see that we have a prompt policy that's composed of a neural network. From this neural network, we can generate some prompt candidates. We run the prompt candidates through the large language models to get the score, the output and the score of these prompts. And based on that, we can update the prompt policy with our reward. So in this sense, we will like attempt to use more of those tokens that will result in better scores. In other words, we're learning the correlation between the prompt tokens and the eventual reward. Yeah. So to make myself more concrete, I can briefly show you the overview of the process. So here we have the prompt policy, which is like a small language model that we keep frozen. We don't really change the language model. We just add an additional neural network layer inside of it. So based on this prompt policy, we generate some tokens. For example, here we have reviewer information or several other tokens. After we have the tokens, we send them into like our downstream language models or even just the API in conjunction with our input. For example, like the sentence we want to classify or the text we want to condition on during our generation. After we get the outputs, we can use these outputs to compute our reward function and use the reward function to update the final prompt policy. So it's a whole cycle. And then I also want to touch upon the reward design because it seems here that like the reward that we compute is very important to how we update the prompt policy. So I want to also talk a bit about how we design the reward. So in this case, if you have some training data, it will be very helpful to simply use the training data and then define the reward function as perhaps some kind of proximity between the output and the training data. If you don't have training data, but you have some idea of how to measure the success, you can develop a metric to measure that success. And we'll actually have an example of that later. In the worst case scenario, if you have no training data, but you have no idea how to measure the success, it might still be possible. Maybe you can learn a metric to approximate human judgment, or there might be some other ways. But in all of these cases, yeah, so these are some guidelines that we can give about how to design these rewards. After that, I will go through some experiments / example use cases of some tasks we experimented on and how we design rewards in these tasks. The first one we experimented on was few-shot text classification, for example, sentiment analysis, topic analysis. And for these, we designed a reward function as sort of a gap between the label probability and the second best label probability. It's a little bit like a hinge loss. I can talk a bit more about the detail if you're interested, but in the interest of clarity, I can skip the details for now. The next experiment is on unsupervised controlled text generation. So here you have no supervised data, but you do have access to, say, two corpora, and you want to transfer your style between your corpora. Say, if you have Shakespearean English and you want to rewrite the Shakespearean English into modern English, you might not want to change too much of the original content, but you want to change the writing style. So the style here is the key. Here we can design perhaps a reward function as like how well the output preserves the content of the input. So that's what we call the content score. And also how well does the output match the style that we're looking for. So there's a style score, and we just sum them all together. Yeah. So based on these, we do have pretty good results. So on few-shot classification, we outperform a wide variety of previous fine-tuning and prompt optimization approaches. So or even just simple prompting. And also you might ask, reinforcement learning is well known to be not super stable and not super efficient. So maybe you just use so much more compute than previous methods. And also maybe your optimization is super unstable. You might just have cherry picked the best result. Actually not so. So you can see on the right here, we have a figure of a comparison between our performance versus a comparable continuous prompt tuning approach. So you can see here that in the same number of training steps, we're able to outperform the prompt tuning approach while being relatively stable. So you can see here. So we experimented with we ran this experiment multiple times, no cherry picking at all. And we visualize like the upper and lower bounds of the performance. So you can see here that even in the worst case, at convergence, our performance is at the same level with the best performance of the prompt tuning. And in the average case, we're quite better. And also going forward to like unsupervised text style transfer, we also outperform previous like fine-tuning baselines as well as prompting baselines. In particular, these fine-tuning baselines, for these fine-tuning baselines, we're using basically the same model, except these training baselines update the entire like hundreds of millions of parameters of the same model, but we still get competitive to even better performance. During this process, we also developed several techniques for stabilizing the reinforcement learning training. And as you can see here, we were able to like we're able to make the training pretty stable. And so if you're interested in the details, you can feel free to ask me any questions or check out our paper or the code base where we implemented these techniques. So aside from the performance, we are also able to analyze the prompt that we use to like derive some insights into how prompting works for large language models. We found two interesting observations. So the first one is that the optimal prompts don't necessarily follow human language. Also, these optimized prompts can transfer trivially across models for similar or even better performance. So the first part here, we're showing like some manual prompts that are well known in the field for this task, and also some in comparison to our prompts, which can get comparable to much better performance. As you can see here, in the manual prompt, all of these prompts are like pretty reasonable for like these tasks. However, they have a wildly varying performance, ranging from like some of the best prompts to like pretty like mediocre performance. On the other hand, with our prompts, our prompts are not necessarily what you would consider fluent human language, but you can still look into it to see what kind of patterns there exist for like what can best prime this model to perform the task that we want. So you can see here that if we want to transfer from a positive sentiment, so maybe a 5-star review, to a negative sentiment, which represents a 1-star review. So turning from like 5-star to 1-star may involve some kind of contrast or some kind of changing like difference. On the other hand, to change from a 1-star to a 5-star review might include some kind of excellent comparison experience. So these seem to be more a better primer for like models to like generate something more positive by transferring the same input. So these are some of the analysis that you can do here, and it might also open up questions as to like how current language models really understand these prompts. Do they understand it like as humans do? So perhaps not. The other part is that because all of our optimized prompts are in the text space, they can transfer pretty trivially across various language models from all the way from like from a smaller model to a larger model, or even from one type of model to a completely different different class of models. So in the figure to the left, we are able to transfer, say, a prompt learned from Roberta to a prompt to like GPT-2 to perform the same task. And as you can see, also we transfer from like maybe a very small Roberta to like a very large Roberta, or vice versa, or the same case for GPT-2. As you can see here, like the prompts we learn from Roberta actually transfer surprisingly well to GPT-2. And also you can learn the prompt from like a smaller model, but apply it to a larger model for even better performance, which is pretty exciting because it tells us maybe there's another way we can optimize these prompts. We can optimize them on a smaller model, but then transfer them to a larger model to get superior performance. Also, you might ask, like maybe manual prompt will just can transfer just as well. And you can see that on the right here that we compare with manual, and you can see that if we learn a prompt for like a larger model and then try to transfer it to smaller models, like it still outperforms manual prompt. The next question you might have is like right now, like a lot of people are using GPT-3 models, which have been instruction fine-tuned to follow human written prompts. Like, what's the utility of even optimizing these prompts to something that's not necessary in the space of something humans might not consider? Actually, I also just ran this experiment recently. So I took the GPT-3 models from API, and I just simply took the prompts that we trained on GPT-2 and just ran them on these models. And I will tell you these models are like instruction fine-tuned. These are instruct GPTs, and it turns out our learn prompts can still transfer even to like these language models that are instruction fine-tuned. So you see here that like these, so like the model, so like the prompt that we learn on GPT-2 still performs pretty well at the same level when we transfer it to like GPT-3 models. So so it tells us that these prompt optimization approaches are still effective even for instruction fine-tuned large language models. And our code and library are available on GitHub. And right now, I mean, we've been having more stars since I last took the screenshot. And then our library is like written to be really modular. There are like a couple of parts of this framework that you can pretty easily just call. For example, in this, this is basically the code that we wrote for running a text style transfer experiment. And as you can see here with our various components, it's able to simply perform the experiment in like 20-25 lines of code. So it'll be relatively easy for you to adapt for your own tasks. And I can also show you some demos of this prompt in action. So as you can see here, that when we generate for the same input, when we don't use any prompt versus we use a human written prompt versus using our learned prompt, there's actually a pretty big difference in like how well these prompts turn out, even though our learned prompts are not necessarily what you consider to be like a valid prompt for this task. Yeah, and so to sum up, so if you are not taking away anything else from this presentation today, so I will talk about some quick takeaways for you to have. So the first part is optimizing these prompts for large language models is still challenging, should be done carefully. The best way to talk to these language models might not necessarily be human language, even though these language models might be fine-tuned on additional instructions. Last but not least, reinforcement learning-based optimization can allow us to find out the best prompts effectively. So that's all I have. Feel free to check out our blog post, paper, code, and API by scanning the QR code here, and I am happy to take any questions.
Thank you, Ming-Kai, for the great talk. It was really interesting. Does anyone have any questions? Mark?
Thank you so much. This was really fascinating. I mean, you were exploring kind of machine ways of generating prompts. Something that interests me is whether different humans have different abilities to write prompts. You know,